Hi! So, just like the Star Trek Next Generation TV series back in the 90s came to an end, also everything else in life must come to an end, and so must this lecture series we have in optics must come to an end. And here I will speak about telescopes, so we will essentially boldly go where no man has gone before and beyond into the infinity, just like Buzz Lightyear was doing in the epic and funny Toy Story movies. So I guess I'm not a Jean Picard, a elegant, smart old British Johnson in the chat, but rather a comic character from a animation movie. But in any case, I will be speaking about telescopes, and why I chose this prelude is that the main application of telescopes nowadays is to actually look into distant objects, such as stars, moons and planets, and even further off galaxies. So we will be looking at the telescopes, and we want to understand how they are being formed, and how they function, and what are their main applications. So when we're looking at telescopes and thinking what they do is that, of course, they are used to image very distant objects. That's the kind of main function when we're looking at telescopes. And in all its simplicity, the kind of easiest telescope configuration we can come up with consists of two lenses, and they are being separated by a distance of d, which is equal to the focal lengths of these two lenses. So essentially, I have a first lens, let's denote that as the objective lens, and then I have a second lens known as the ocular or eyepiece, and that will be having the corresponding focal length of Fe. So here the objective forms essentially a demagnified intermediate image of an object, and now my object is far away since I want to look distant objects, and it will essentially form an image at the focal point. Recall the thin lens equation, we really see that when we put an object at infinity, we have an image at the focal point, FO, of my first objective length. And now this intermediate image, well, it is also formed at the front focal plane of the eyepiece lens, so that would be our second lens here, since I'm placing them at the right distance of d, which equals the sum of the effective lengths or focal lengths of these lenses. And now what I have at the end of the day is that I have a final image formed at the infinity, so after the eyepiece I do not actually have an image formed, but rather it will be formed at the infinity. And this kind of lens system, when we're looking at it, it doesn't have a front focal plane, it doesn't have a back focal plane. Please remember what was the definition of front and back focal planes. So this kind of lens system is known as a focal system. So essentially, like if I have my rays coming at infinity, and when I'm looking at what comes out, I do not have rays converging into any given point, so it doesn't have a back focal plane. And the same thing applies if I would look at the rays coming at infinity now from the image space. I see that no front focal plane is being formed, so that the rays do not actually tend to converge anywhere, but rather they will just shoot out straight along the optical axis. So this is the kind of meaning of being a system that is afocal, just like the name suggests. Now, let's look next how we can understand how much a telescope actually magnifies my distant object. So let's look into the kind of collection of rays in similar way as we did with the magnifying glasses, and then want to understand how we can understand the magnification of my system. So let's consider a collection of rays as shown in the figure. So let's look at the kind of bundle of rays. They come at a given angle alpha u into the objective lens, and then they form an image at the intermediate plane. And here it's important to know that this size of my image, YO, as an objective image formed by the objective lenses, this is not zero anymore, so that they arrive at some angle. And now the angle that has been formed is the alpha u, and this is roughly a tangent of alpha u, since we are assuming that we have a small angles in question, and this certainly will be the case when we are looking at distant objects that are relatively then small, since they seem to be at a near horizon, or it could be even just a kind of a moon orbiting some kind of planet in our solar system. So the angle is small, then the tangent of an angle that is small is essentially the angle in itself, and then from the kind of geometrical considerations we know that then we can take the tangent of this angle alpha, and then we can calculate with the y divided by the effective focal length of my objective length, FO. So this is how I get the angle that is being used, or is essentially the angle that the bundle of rays coming into the objective lens make. And now these rays form the intermediate image, and now what happens afterwards is that the eyepiece, known as the ocular lens, then forms an image in the infinity out of these rays that then come out of this intermediate image. So now I'm looking at how eyepiece images things, and now instead of having the intermediate image, I'm assuming, I'm thinking that this is now my object, and then I'm thinking how the image will be formed. And now I want to see what will be the new angle alpha A here, and how that relates with the original angle, because then the ratio of these angles gives me a magnifying power. In other words, the transverse magnification of my system. So the alpha A is, again, we apply the small angle approximation. It's approximately the tangent of the alpha, and the tangent of the alpha, we can look at the image here. This angle equals to the angle in here, and then I'm essentially be able to calculate the tangent of alpha A as the ratio of y with respect to the focal length of the eyepiece. Now we can calculate the magnification, MT, or magnifying power, the same thing really as the ratio of these angles used. And here, essentially, I can simplify that, so I can even find that the ratio equals with the ratio of the focal length. So essentially, it's the ratio of what is the focal length of the ocular versus the objective lens versus the focal length of my eyepiece. So we see that the magnification really clearly depends on this ratio of the focal length, and thus I can easily imagine that if I want to change the magnification of my telescope, I can consequently form different kind of telescope using different kind of lenses, and that's it. Then I can change the magnification. Now let's look into a few different simple configurations next to understand how things look in practice, or how they used to look a few hundred years ago, like back in the 1600s. Basically, I guess that historically a negative lens was used as the eyepiece. So this is known as the Galilean telescope, and it was invented by Galileo, or at least the first time somebody successfully made such kind of telescope configuration. It was done by Galileo, and this is how it looks like in the figure. So we have a positive focal length for the objective lens, and then we have a negative focal length for the eyepiece. So it's basically a concave lens. And now the nice thing is that the separation between the two lenses can be reduced, so that it's going to be a more compact device. The nice thing also is that the image that will be formed is upright. This is the benefit of using a negative focal length lens, so that these are really the advantages of this Galilean telescope. The trouble here is that the exit pupil of the instrumentation is actually inside the instrument, so that if you want to use it for a longer time, it will be a little bit cumbersome, so that you need to position your eye in a very nice way here, and then you also need to squint a little bit so that you get the kind of best possible view out of your system. So that this is actually not the easiest configuration, so that you need to align it quite carefully with respect to your eye. But the benefits are clear, so that the image is upright. So for example, if you would be using this kind of telescope to look, let's say, a boat on an ocean, it would be easier that you see the boat upright, so that the image is not looking the other way around. And then, of course, the instrumentation is compact, because the separation between lenses can be reduced, because we have a negative focal length here. So this is the two advantages, but the use is cumbersome, so that it's not the easiest possible configuration that was used back in the days. There's another configuration that came afterwards, and this was invented by Kepler, and hence it's known as the Keplerian telescope. And here the Oculus lens is a positive one, so then the configuration looks like this, as we already were looking in the first slides. So now the disadvantage is that the separation between the lenses is larger, so it's not as compact device, and the image is actually inverted when you look at it. So that if you want to look objects on Earth, how other sails for us or other boats would look like, then it would not be as nicely used. But of course, this is perfectly okay if you're observing, let's say, stars or planets or moons. Then it doesn't really matter which way you're looking at them. So this is perfectly okay in that respect, depending on the application. The nice thing here is also that the exit pupil of this instrument is outside, so that it's more easy to use. Alignment is more easy with respect to your human eye, so that this is definitely a benefit. The trouble here is, of course, is that we have lenses and they have spherical aberration if you make them spherical, and certainly because of the dispersion of glass materials, they have chromatic aberrations. So these were the kind of my main disadvantages. And a good side note here that if you know what binoculars are and have used them, many times they take use of the Keplerian configuration, where finally the images are being turned upright by using prisms. So this is a very common configuration. You make binoculars using this configuration. But not all binoculars use this configuration, but many of them do, so that they might be a good thing to remember. And here, in connection with the previous lecture on prisms, we see here that they are actually being used to upright the image, so that that's the kind of like one advantage and one use of using prisms, making optical instrumentation. And now finally, let's look into the kind of downside of both of these two simple configurations. The main problems of these two above illustrated configurations is that they take use of lenses. Lenses are dispersive components, and this means that they are susceptible to chromatic aberrations. Essentially, different colors of light propagate slightly differently, so that the refractive index profile, even though it almost is a constant for different wavelengths, it's not exactly so, and because of these chromatic aberrations are being introduced. So this is the downside when you're using dioptric devices, so basically devices that take use of lenses. So different colors form an image into slightly different locations, and this in overall makes the images blurry. And this was a real issue back in the 1600s, and Newton came up with a kind of solution. If I read my history correctly, it's not entirely clear what were the kind of real motivations for Newton to come up with this configuration of using mirrors. Maybe it was also related to this revelation he had regarding white light, so that he was seeing that every white light seems to be formed out of different colors, so he was testing and experimenting with prisms. So maybe using mirrors to make a telescope was also related to this, so that he wanted to kind of double check if the kind of rainbow coloration was actually caused by dielectric materials, so using glasses, or was it more fundamental to kind of image formation processes. But nevertheless, like, we do not know what were the reasons why Newton came up with this telescope configuration, that he nevertheless came up, and then he designed a mirror system looking like this. And there the kind of benefit is that it's not a dioptric system, so it's not based on lenses, but it's rather catoptric, so it's based on mirrors, and here there's no chromatic aberrations present when an image is finally being formed. So now the objective lens is essentially these two mirrors, then my eyepiece can be still a lens, it could be also just a mirror thingy here, and then I get an image finally that is not as much plagued with chromatic aberration. If I remember it correctly, Newton came up with this design and construction in 60-something, and then soon after he was actually awarded a fellowship of the Royal Society Academy of London or something, so that it was actually one of those great inventions of Newton that made him like quite famous. And I think he was using spherical mirrors at the time. I guess polishing a mirror surface was very difficult and things needed to be done by hand. A better configuration would be to use a parabolic mirrors here, but I think he was using spherical mirrors so that even though there was no chromatic aberration, there must have been quite a lot of spherical aberration. And if I remember correctly, there's also a coma aberration present when you make these kind of simple mirror configurations, so that even though it was a huge discovery, it made things better, but nevertheless it was not the kind of most optimal configuration yet, but rather it was a kind of starting point to start designing other kinds of mirror-based systems, so cathodic systems, and even combinations of dielectric components or lenses and mirrors or dielectric elements. So that would be the kind of way to look forward if you want to read more of this. But in any case, chromatic aberrations can be dramatically reduced with this Newtonian configuration, and even though it also has its disadvantages, so there's other kinds of aberrations present, it was a huge progress at the time. And led people to kind of come up with the other telescope configurations. And when we're looking at the kind of modern telescope configurations that exist out there, they are more or less based on this idea and the idea of using lenses. That in the end, when you want to make meter-sized lenses, they tend to be quite heavy and bulky and difficult to use, not to mention polish. But this is what I wanted to say to you in my very last lecture. I really hope that you have enjoyed your ride at the show this far, and I really want to congratulate you in making it this far. I do not know how difficult it is to listen to my lectures, but somehow it shows that you are a brave person and you must have really strong curiosity about these things regarding optics, since you're following me all the way to the final end and into the rabbit hole. So I congratulate you. Please have a pleasant rest of the day and rest of the week, and please join me to listen to my other courses that I'm lecturing. For example, I have a course on solid-state physics, so that might be also interesting and maybe even sometimes joyful lecture series to follow up in case you're interested. So thank you to you, and bye-bye.